Today's paper is SegFormer, simple and efficient design for semantic segmentation with transformers. The proposed model is a simple and efficient transformer-based semantic segmentation framework. There are two core ideas. The encoder in the model outputs multiscale features, and the MLP-based decoder aggregates these information from different layers to output a segmentation map. The model achieves mean mIoU score of 50.3% on ADE20K dataset and 84% on Cityscapes dataset. Now, this figure shows the proposed framework of the SegFormer. Left section shows the encoder part of the model, and on the right we can see the decoder part of the model. Let's first look into the encoder part. An input image is first divided into 4x4 patches, like it's done in vision transformers. But note that in vision transformer, it uses a patch size of 16 by 16. But here we used 4, and using a smaller patch size of 4 in SegFormer makes better dense prediction task. So the authors used a patch size of 4 here. And now, looking at the transformer block, we see that it's composed of 3 sub-modules: efficient self-attention, mixed FFN, which is feed-forward network, and overlapping patch merging module. The first efficient self-attention module works like original multi-head self-attention in transformer, but uses a sequence reduction technique to lower the computational cost. And the next block, which is mixed feed-forward network, is used to solve the fixed resolution problem. Instead of using fixed-sized positional encoding, layers of convolution and MLP, multilayer perceptron, is used to implement data-driven positional encoding. And the last module, overlapping patch merging block, is used to reduce the size of the feature map. As we can see in the figure, feature size after going through this module, we can see that the size of the feature is reduced as it goes to the higher part of the network. The decoder part is simple compared to the modules in the encoder. In the encoder part, we see that there are different features of different sizes in each layer. The MLP layer in the decoder, it's a full MLP, and this takes the features from the encoder and fuse them together. This all MLP decoder is composed of 4 main steps. First, multi-level features from the encoder. It's fed into the multilayer perceptron layer to unify in the channel dimension. Then the features are upsampled to 1/4 of its size and are concatenated together. Third, a MLP layer is adopted to fuse the concatenated features. Finally, another MLP layer takes the fused feature to predict the segmentation mask. Now, this table shows the performance of SegFormer on 2 datasets, ADE20K and Cityscapes. Compared to other state-of-the-art models, SegFormer achieves best performance on both of the dataset. On ADE20K, it achieves mean mIoU score of 51.8, and on Cityscapes, it achieves mean mIoU of 84%. It's on the bottommost row here. The model also works well on real-time settings. It's shown in the top table. The parameter size of the model is lower compared to other models. It's 3.8, should be million here. And it's lower compared to other models like FCN, ICNet, PSPNet, and DeepLab v3+. And yet it achieves a good performance. It's actually higher than all other models. Let's see, ADE20K here, we can see that the mean mIoU is 37.4. That's compared to Deep Lab v3, it's about 3% higher. And also in Cityscapes, it's showing good performance as well. Link to the paper and some useful resources will be provided in the description. That's all for today, and I'll see you next time with a new paper.